There, hopefully. Because this might be on the quiz. Thrust versus drag, lift versus weight. Thrust makes you go forward, lift makes you go up. Any questions? That's a much better airplane than I am able to draw. At least it's got 3 wheels. Alright, this is just a different diagram of the same thing. You notice thrust is pulling the airplane forward, drag is pulling the airplane backward, lift is trying to lift it up, and weight is trying to pull it down. Yeah, we don't care about that. Alright. So, if you want to generate lift, you got to have 2 things. You got to have some air, and you got to have some motion between the air and the airfoil. So we're going to add 3 things. We're going to add one to that. You got to have an airfoil. You got to have an airfoil, you got to have air, and you got to have air moving over the airfoil. That's 3 things. That's a really good test question. Quiz question. What are the 3 things you need to make lift? You need air, you need an airfoil, and you need relative motion between the 2. Or you could say the third thing, instead of relative motion, the air has to move across the airfoil. That's propellers just pull the airfoil, the wings. You got to pull the wings through the air. Or if you're flying a helicopter, you use the engine on the rotor blades, and the rotor blades are the airfoils, and the airfoils, the rotor blades, make the lift. Airfoil is spelled A-I-R-F-O-I-L. It's like aluminum foil, except it's made out of, well, actually, wings are made out of aluminum. So I guess airfoils are usually made out of aluminum too. So there's 2 people we're going to look at that describe how this works. And one of their names is Newton. So I'm going to spell Newton. And Bernoullis. And both of these gentlemen were experts in physics. How many people in here have taken a physics class before? 1, 2, yeah, I took physics my junior year in high school. A silly person. There was 2 of us who were juniors, everybody else was seniors. They didn't harass me that bad. I only got beat up like once a week by the seniors. Not every week, just most every other week. All right, I don't care about that one. All right, what I do care about this one. Newton's 3rd law of motion is that for every action there's an equal and opposite reaction. So it's the 3rd law. That Newton's 3rd law says, I don't care about this. Newton's 3rd law. For every action there's an equal and opposite reaction. So what that's trying to describe here, and you might just want to draw this airfoil, is that if the airfoil is going this direction because of thrust, thrust is pushing the airfoil back. The air is hitting the wing, and the air is deflected downward. In this case, it shows it's getting deflected in this direction. So if this is lift, so if we push harder on the bottom, I know this is going to be pretty hard to think, but if you're holding a box in your hand and you push up, which way direction does the box go? Usually up, unless you're weak and you're not as strong as the weight of the box. And then the box goes down even though you're pushing. But generally, if you're strong enough, you can push on the box and it goes up. So one way to get lift is through Newton's 3rd law of motion. The air hits the wing, and the wing is forced downward. Newton says every action has an equal and opposite reaction. So if we push air down, it's going to push the wing up. And we're going to talk about it before today is over some more. But if the air is coming in at this direction, but the wing, you'll notice, this direction right here, there's this angle right here. This is called the angle of attack. I'm sure you're writing that down. That's the angle of attack. And the angle of attack is the difference between this relative air and the chord line of the wing. If we put a line through the tail end of the wing and it came out right out the front of the wing and kept going, so we extend that chord line, this is the angle of attack. So think about it when you're driving along in your car and you stick your hand out the window. If you stick your hand out straight, then the air hits it. It doesn't do too much. But if you angle your hand up a little bit, it starts hitting your hand. It does push your hand back, but it also lifts your hand up. Pushing your hand back, that's drag. But lifting your hand up, that's lift. So according to Bernoulli here, if there's every action, there's an equal and opposite reaction. So some air is trying to push the wing backwards, isn't it? So that's called induced drag. Induced drag is any drag that's caused because of lift. So here we're going to have, so if we have thrust going in this direction, we're going to have drag in the opposite direction. We're going to have induced drag. And induced drag is drag due to lift. If you're getting lift, you're producing drag, and this is called induced lift. There's another kind of drag at this moment. It's called parasite drag. It stick an antenna somewhere, it has drag. If you have landing gear sticking out, all these other kinds of drag not cause any lift to occur. I don't care about the kite over here. Anybody going to go fly a kite? You can draw that one. Anybody ever see that Mary Poppins movie? At the end, everybody gets together and sings that song, Let's Go Fly a Kite. It's kind of like a Bollywood movie, where everybody dances and sings. Anybody seen movies from India? I mean, they don't all at the end have everybody singing and dancing, but a lot of those movies has everybody sing. Okay, well, it's not quite the same with Mary Poppins because it was made in England in the 1960s. But, okay, fine. Has anybody ever seen Mary Poppins, the movie? 1, 2 people? Obviously, you are 3, 4 now. Finally, you raise your hand. Okay. It's the one with the umbrella. She can fly. She's not on drugs, and she's not a helicopter. She's got a magic umbrella. She pops that thing and just whoosh, takes off and goes cruising, man. It's not as good as Superman. She can't go supersonic and stuff. But not bad for a little old lady with an umbrella and a little red black hat. All right. I don't want to do that one. I don't want to do that one either. All right. The next one I want to talk about is Bernoullis Principle. Bernoullis Principle states that, I don't care about the word states that. In a closed energy system, no energy is lost or gained. Energy is only changed to a different kind of energy. So Bernoulli was a physicist being someone who studies physics, just like Isaac Newton. Sir Isaac Newton, does anybody know what he's famous for? Like about 17 things? Go ahead. The law of gravity, he described it. Everybody knew there was gravity, they just didn't really know what it was. The rotation of the planets and orbits. He actually invented the math to calculate how fast the planets were going around the Earth. And in fact, he called it calculus. So if you take a calculus class and you don't like it, you can blame Sir Isaac Newton because he invented calculus. I took calculus in college. I got a D. I think I got a D+ in that class. I didn't do the homework. It's all my fault. I accept full responsibility. So I want to show you an example. And so let's talk about a venturi. So here is an example of a venturi. So this here is a venturi. And I'm sure you're going to draw one on your notes. And let's say we're blowing air through here and it comes out the other side. This also works with water. It works with fluids. And when I say the word fluids, I'm talking about fluid air and fluid liquids. This doesn't work very well with solids. So closed energy system means that there's no holes in it. Air cannot escape. Once we stuff the air into this end on this end, so here's a hole on this end. Once we stuff the air in here, it can't get out until it goes out the other side. So all along here, there are no holes in this tube, and there's a restriction in the tube right here. It gets smaller. So I want you to think about it. What happens, has anybody ever come out in the front yard or the backyard or your neighbor's yard or someone you didn't like's yard, and you turn on their water hose and you put your thumb over the end of the hose? What happens to the velocity of the water coming out the hose when you stick your thumb across it? The velocity goes up. It's because you've caused a restriction. Well, literally, if here's a water hose and you stick your thumb across it, I personally like black fingernail polish, the water's going to come out, but look what you did. This part right here, you just turned it into a Venturi tube. So the velocity goes up. So the same thing here. If we were measuring the velocity right across this point right here, the velocity gets faster. And then, as it gets bigger again, the velocity is going to go back to the same. So we start out with a certain velocity, the velocity gets faster, and then when it comes to the other side, the velocity stays the same. Bernoullis says that if this is a closed energy system, no energy is getting in, no extra energy is getting out, that the energy doesn't disappear, it just changes into a different kind of an energy. Well, what's going on here? We have energy due to velocity right here. That means we have to take energy out of this air in some other form, and that's in the form of pressure. The pressure goes down. So inside of this Venturi, we start out with a certain pressure, we restrict it. The velocity goes up. So that's a kind of an energy due to velocity. But so is pressure. So we can change it from pressure energy to velocity energy. And then when it exits the Venturi right here, the pressure goes back to where it was. So at any given point in this system, whether it's right here, or it's right here, or it's right here, the energy is the same at any of these 3 points inside of this Venturi tube. We haven't added energy to the air, we haven't subtracted energy. All we did was change the energy from a pressure to a velocity, and then after it gets through the Venturi, it's back to where it was. So all we're doing is trading velocity for pressure or pressure for velocity. Did I lose anybody there? So on the test, you need to be able to draw a Venturi and tell me what happens to the pressure and the velocity in the middle of the Venturi. And you need to tell me that as long as it's a closed energy system, the total energy is the same at any given point. Did I lose anybody there? If I've lost you, remain seated. Okay, I'll say it again. Just kidding. These two things here are the basis for how an airplane gets lift, or a rotor blade on a helicopter gets lift. We're going to make, I don't care about these kids. There we go. So here, let's look at Bernoullis Principle here in a wing. And the way I look at it is that, look, here's this Venturi. It doesn't work as well if we only have one, but it still works. So air comes along here, it goes across the bottom. Air goes across the top here, and here the air is forced to go faster. So the velocity goes up, and the pressure goes down on top of the wing. The pressure down here stays relatively constant. The pressure here doesn't move. It doesn't get higher, the pressure doesn't get lower. But especially right in here, and actually the biggest pressure is right around in here. This is where the velocity goes up the highest and the pressure goes down the most, is about a third of the way down the wing. This is also called the center of pressure. If you were going to say, where is this lift acting on the wing, it's about a third of the way back from the front of the airfoil. And in fact, in that wing, that's generally, and I put a half there, sorry, that's really a third. That's really where, if you were going to build something strong on the inside of it, it's called a spar. You don't have to write spar down. But that's where they generally put the spars, about a third of the way back, because that's where all the force is, lifting the wing up. And of course, you got to bolt the wing to the fuselage, because you want to get everything in it connected to it. So this is just half, but it still works. We're forcing the air to go faster. The pressure gets less. The pressure gets less, so because the velocity goes up. So I would expect you to be able to, on the quiz or the test, is draw a lousy airfoil and draw the fact that the pressure stays the same, and if you want to use a line going sideways for the same, that's okay, or you could write the word pressure stays the same on the bottom. But on the top, I would expect you to be able to label that the air on the top of the wing, the velocity is getting higher and the pressure is getting lower. So this difference in pressure, so is the pressure on the bottom or on the top higher? I know this is tough. Look at it for a minute. Don't say it out loud. Mauricio, which side of the wing, the top or the bottom, has a higher pressure? The bottom, that's correct. So, Josh, why is the pressure on the top of the wing lower than the pressure on the bottom? Well, the bottom pressure isn't getting affected according to this diagram, right? Okay, so why is the pressure on the top of the wing lower? Why did the pressure get less on top? Because it's flowing. So can you describe more specifically how is it flowing compared to the air under the wing? Is it going faster or slower? Faster, yeah. The airflow on top of the wing is going faster. The pressure is less, yeah, I know. Higher velocity means lower pressure. Okay, so the last one here is, tell me, where is the center of pressure on a typical airfoil? Jaron. It's approximately located how far down the wing? I know I covered it up with my red marks. Brian? Approximately 1/3 from the front. The center of pressure. And so that's where they put the big chunk of metal inside the wing, because that's where all the force is. When I say they, I'm talking about an aeronautical engineer. Anybody in here want to be an aeronautical engineer? It's really fun. You get to do calculus. How many people in here have done calculus? 1, 2, 3 people. How many people like calculus? Okay. Did it change you psychologically, Jonathan? Are you a different person? Okay. All right. So this is just a nice diagram. It shows a wing. The airflow on top is faster, so the pressure is lower. Higher pressure on the bottom pushes the wing up. Okay, I don't care about that. And I don't care about... Well, let's look at this for a moment. So this is trying to show the fact that this, if you look at this yellow line right here, as the air is leaving the back of the wing, the air is going down. So is that due to Bernoullis Principle, or is that due to Newton's third law of motion? Brandon. You got a 50-50 shot here. The airflow, I know it's hard to see, but the airflow is actually going down right here. Is that airflow going down because of Newton's third law of motion or because of Bernoullis Principle? Newton's third law, that is correct. So the next question is, explain to me Newton's third law of motion, Jordan. You can do it. What's Newton's third law of motion? For every action, there's an equal and opposite reaction. So if this air right here is flowing down, is getting pushed down, if this air is getting pushed down, I know it doesn't look like it's going down much, but this air is going down. What's getting pushed up, Jordan? Try again. What thing? If the air goes down, then what gets pushed up? Not gets higher, but what gets pushed, literally. There's now a force. No, it's not pressure either. What's the other thing that's in this picture besides air? What's that big white thing? Yeah, the wing. So if the air gets pushed down, what gets pushed up? Jordan? The wing, yeah, or the airfoil, either way. The airfoil is the wing. The wing is just a type of an airfoil. The rotor blade on a helicopter is an airfoil. The tail rotor on a helicopter is an airfoil. A propeller is an airfoil. It's just which direction. Well, and is it going to make lift force or is it going to try to thrust? So like in an airplane, the wing is an airfoil and all we want it to do is make lift. If you have a propeller on it, it's an airfoil, but all we want it to do is make thrust. In a helicopter, the rotor blade's on top. We want it to provide lift to get off the ground, but we're going to actually tilt it in the direction we want to go. And that same rotor blade that generates lift, it also generates thrust. So in all cases, we're talking about airfoils. Yeah, Jonathan? Who creates a ceiling fan? A mechanical engineer in a very small room. Probably in a foreign country. I don't know how many ceiling fans are made and designed in the United States. There's probably a few. There's some minor research, but let's face it, how efficient do electric fans have to be? What if they're 3% less efficient than they could be? Will anyone ever notice? Probably not. The only time you might notice, not in a ceiling fan you probably don't notice, but maybe a fan in a large building that houses 3,000 people. If all your fans were 3% less efficient than they could be, your electric bill is going to be higher than it would, right? So in that case, you might want to buy really well-designed fans to blow air around. But in your house, it's not like you're going to go out and measure the efficiency of the fan blades. In fact, I think most ceiling fans are designed to look pretty, not to be aerodynamically efficient. Did I answer your question okay? All right, so here is a diagram that's effectively saying both of these things. Here we have an airfoil. It happens to be a wing. You notice that we have, if I can find it here. Here we have relative wind. And if I take a line from the tail of the wing, the trailing edge, and I run it through the leading edge, the farthest most spot, and I keep extending that. This angle right here, don't say it out loud. The name of this angle is, don't say it out loud. The name of this angle is, Jonathan, the angle of attack. So the wind hits the wing, and some of it, I don't like the fact that this arrow's down. It really gets deflected down like this. But if this relative air goes down in any way, then the wing is going to go up in some direction. And of course, if we have faster air across the top, if we have a high velocity, then we're going to have a lower pressure, but the pressure down here stays the same. Lower pressure than the bottom. The bottom is now going to push up because we have higher pressure on the pressure on the bottom stays the same, but the pressure on the top gets less. So we're going to have an increase in the difference between these two pressures. So this is really just a combination showing Bernoullis Principle and Newton's third law. Jonathan, question? Yes, this applies to propellers underwater. There's a few other differences, but yes, this is the same. I think the shapes are different and how fast you can spin it, and there's things called cavitation. And there I have just exhausted my knowledge of marine propellers. Oh, they spin. I know that much. And they have blades on them. Woohoo! I knew more about marine propellers than I thought. And the faster you spin them, the more noise they make. So if you're in a submarine and you don't want people to know where you are, you make a really big blades, but you make this propeller spin slow, and it doesn't make as much noise.
Is that the only way to get thrust in water?
No. Is there another way to get thrust? Surely there is. I don't know what it is. I don't know. Don't jet skis? They don't have propellers. But they've got some kind of a water pump inside the machine, but I don't know how that pump works. I think it runs off of a former motorcycle engine, and it burns gasoline. Unless you have an electric jet ski. I don't think anybody's had an electric jet ski yet. All right, I don't care about that either. I don't care about that one either. All right. All right, one of theirs on there. Well, let's see. I'm going to wait for it to stop. Being stupid here. If you wear white shirts with epaulets, you too can design the airfoil shape. See how they got their little white epaulets going on right there, but nothing on them? Look, it's a blue name tag. See this? I bet you this is Civil Air Patrol cadets. If you want to get some free flying, you can join the Civil Air Patrol in Fresno. They get you uniforms and you get to march around. But they have ground schools, and the first they teach you how to be an observer and ride in the back seat, and then they let you sit in the front seat and take flying lessons. They got a 182 in Fresno. It's 4 seats, but it goes about 150 miles an hour. It has a variable pitch propeller. Okay. I'm tired of waiting. Yes, question? Yeah, go ahead. Don't bleed on the floor. That's worse than eating in here. I failed to put that in the syllabus, obviously. No bleeding in the classroom. Okay, it'll start one of these days. Yeah.
How long does it take to make these PowerPoints?
It depends on whether you copy somebody else's first. The question is, how long does it take to make the PowerPoints?
Or this PowerPoint you made?
Not that long. No. All right. Actually, what I want to talk about for the last few minutes is I want to talk about lift. Do I know when the essays due in the other class? I'm pretty sure it's Thursday. Yeah, which Thursday? The one that's 3.5 days from today? Just for fun, since you asked, I'm going to look it up in my copy of the syllabus. You know, just like the copy that I passed out in class on the first week of school. Flight 102, Essay 3 and Research Project due 5 October. 1, 2, 3, 72 hours from now. Don't worry, you spend like 5 of the next 72 hours on it, you'll have it done. 5. Okay, so the last thing I want to discuss before we end class is factors affecting lift. Is that on like near the bottom of the page? Okay, ways to change lift. Fine. Ways to change lift. So number 1 is the size of the airfoil. So if we make an airfoil that's this big, let's say here's an airplane with a wing, and we take the same airplane and we put a really big wing on it, and we do the same thing to it, fly it through the air, the one with the bigger wing gets more lift. Hopefully this is reasonably intuitive. Say that again? Yes, the speed will impact it, but at the moment, fine, that's number 2. Yes, the speed will impact the wing. What was it? There was another question there? It would create more drag. You could also make the wing bigger like this. So when I say bigger, I'm not just talking about, it doesn't have to be how long it is. It could be how wide it is. It just has to have more area. So Rodrigo had a good thought there, and it is yes. The speed of air. Remember the 3 things we got to have. We got to have an airfoil, we got to have air, and we have to have motion between the 2. So if we have an airfoil and we blow air across it, and let's say it's going 100 knots, and let's just say for fun that the lift is 1,000 pounds of lift. If we change this to 200 knots, woohoo! It's not exactly 2,000 pounds of lift, but it's really, really close. We're not going to get into the formula today. But the faster the airfoil goes, the more lift it gets. Jonathan? With the lift formula. We calculate lift with the lift formula. Can we do that tomorrow? I really want to get to number 3 and 4, and I'm trying to do it before I forget. Does anybody have any other ideas about what could change how much lift you have? Yeah, go ahead, Jonathan. The angle of attack, it's like we talked about that today. Yeah, the angle of attack. And watch out, some people are going to call this AOA, angle of attack. That's very common in aviation. So if we have the relative wind, and we have one airfoil that has very low angle of attack, and we have another airfoil, which you can't draw correctly. It's the end of the world as we know it. So 3 is angle of attack. So here's our relative air, and we have an airfoil, and here's our relative air, but we have an airfoil at a high angle of attack. So this is going to be more lift. Hopefully you can draw better on your notes than I can draw with my mouse tablet here. So let's see, just for fun, who can tell me why having more angle of attack means more lift? And let's see, round and round she goes. Where she stops, nobody knows. Jordan. This is you had your lucky day the first day I did this, didn't we? The air goes, you were talking about the air going under the wing, yeah. So if there's a higher angle of attack, what happens to this air that's different than if we had a low angle of attack on the left? It pushes what? It pushes the wing which direction? Up. Yes, it does. So if we have more air hitting the wing, is it going to push the wing up more or push the wing up less? It's going to push it up more. Again, this is like sticking your hand outside of the window when you're driving in the car. So I'm not going to give away any money, but does anybody know what number 4 is? Okay, 3, 2. How thick is the air? What's the density of the air? So effectively what that means is if your air's speed is the same and it's at the same angle of attack and you have the same shape of the wing and you're flying at a high altitude where it's less dense, you'll get less lift. So the only way to make up for that is to go faster. Or, question? Faster. Well, in flying airplanes, it's almost always better. Can anybody think of a time when flying faster is not better in airplanes? Landing, yeah, when you're landing slower is better as long as you don't crash the plane. Yeah, as long as you don't lose lift to the point that you fall down. So there's going to be some minimum speed. Like on an airspeed indicator, the bottom of the light arc is for fun, I won't go get that. Yeah, what the heck, I'm going to go get that. On an airspeed indicator, the bottom of the white arc. What's the bottom of the white arc on an airspeed indicator? I know it was last week. Let's see if I can pull Jordan's name out again. Josh. You don't know? Have you ever seen an airspeed indicator? Okay, so there's a green arc and a white arc and a yellow arc. The white arc whatsoever? When the white plane what? No, it's the airspeed indicator with the it's labeled in white or labeled in green. You don't know anything about the white arc? Okay, it has something to do with the flaps. Does that help? Okay, at this rate, you're going to do really poorly on the test. I'm sure you'll study notes from last week more than you have so far. Johnny, can you tell me anything about the white arc indicator? It's the flap operating range, yes. So what's the top of the flap operating range? Correction, it's the high end, the highest airspeed on the white arc. Do you know what that means? Do you know what that is? I'll give you a hint, it's VFE. Right, it's the maximum velocity that you can have the flaps extended. So if you're flying along and the white arc goes up to 100 knots and you're doing 110, you can't put the flaps down yet. You got to slow down first to below 100. Now, what's the low end of the white arc? What's the airspeed that the white arc is? You know what the name of that is? Oh, wait, I got to ask somebody else. Like Rodrigo. The low end of the white arc. I know you'd rather fly helicopters than airplanes. And helicopters don't have white arcs because they don't have flaps. They don't even stall, so they don't even have green arcs. Red lines, though. The lowest speed before you can what? Yeah. With speed you can fly with the flaps. Well, you're on the right track. So what would happen? Let's say you go a little bit. You have the flaps extended all the way out, and you're getting slower and slower and slower, and the airspeed's getting less and less and less. And you go to the bottom of the white arc, and then you go 2 knots below it. What will happen? What will happen if you have all the flaps out and you go slower than the white arc? You're not going to get more lift. On the contrary, what's the opposite of getting lift in a wing? When the wing... A stall. So we're going to talk about stalls tomorrow. Let's see. It's 16 after in real life. So 26 after on your cell phone is when class will start back up. I'll be right with you.